Hello everyone, my name is Atmani, and today I'm going to present you my risk project, Foresight-Bench, waypoint generation method and benchmark for embodied VLM-based long-range path planning. And I would like to start the presentation with a quote from William Blake. Hindsight is a wonderful thing, but foresight is better. And this quote kind of sums up the motivation behind long-range path planning. Let's imagine ourselves being in the middle of this field and trying to reach the goal on the left. We wouldn't just go straight into the forest, kind of try to find our way around through all the bushes and the trees and then reach the goal. We most likely would just detect the forest beforehand, kind of use this indication and therefore proactively plan around it. And this is the advantage that long-range path planning provides. But most systems or current planners that rely on LiDAR and stereo are limited to short horizons. So therefore, we cannot utilize LiDAR or stereo like these in order to get these advantages that long-range path planning provides. So therefore, we are kind of limited in using RGB cameras because they provide longer horizons, up to 500 meters, but also have the benefit that they provide us a lot of semantic information. But how can we utilize these kind of semantic information for our proactively plan? And there is VLM. VLM is the kind of jack of all trades in this case. The VM is multimodal, it's flexible, and does not require any training beforehand. So let's take this example. We prompt a VLM to kind of stay hidden in order to reach a goal, and we see it does it successfully. And when printing out the justification, we see that the VM kind of shows an understanding that being behind trees provide cover. So this is a good indication for us to utilize VM in this kind of image space planning in order to have a more generalizable and flexible long-range path planning. But how exactly can we do that? Well, there's been some research in this field, and a common way to bridge spatial coordinates is by giving the VLM an image with waypoints or set marks. So meaning we give the VLM this kind of annotated image without the paths, and it kind of tries to utilize these waypoints that are given in order to reach the goal. And this is something that we are using, but um, we see that we cannot rely on possible waypoints markers being given forehand. What do I mean with that? So let's take a look into this example. So we see in the manual kind of waypoint generation, meaning that the human operator individually set these points that the VLM performs very well. Because the kind of waypoint placement is very good because they are embedded with heuristic, meaning they are semantically uh, very good or provide a lot of information in the sense that the VM can utilize its prompts. Whereas when we see this kind of sampled version where we utilize blue noise sampling, that the path is kind of not very well. This is because the blue noise sampling and therefore the placement of these waypoints do not respect the prompt, as for example, trying to reach the goal there by being on the sidewalk and then crossing. So we see that the waypoint generation and these kind of VLM planning plays a crucial role in the VLM's performance. So therefore, the question arises, how can we best create long-range plans that respect the task prompts given? And we propose an iterative segmented kind of way. The high-level idea behind this is, first of all, to utilize segmentation in order to ground and contextualize the VLMs and its prompts, because we do not want to have some waypoints that are kind of in the sky and the VLM chooses it. We want to have a reasonable choice of waypoints through the VLM. So therefore, the segmentation kind of ease up the process for the VLM. Also, we want to kind of have it iteratively. So meaning without kind of having all the waypoints first, we want to have or want to give the VM the chance to kind of plan it incrementally with a feedback loop, meaning that it knows where it has been and therefore have a more coherent reasoning in its path. And lastly, we want to give with this kind of iterative approach the VLM more degrees of freedom, because we saw in the sampled version that that when the points are set without like any uh, VLM's participation, that it kind of limits the prompts and the kind of semantic clues that the VLM can leverage on. So therefore, we want to have it more independently, give the VLM this kind of chance to choose its own waypoints. But how does it look in detail? So the kind of approach is we have a raw image with start and end point, kind of pre-process it with grounding SAM, meaning we segment it and mask it and have this kind of image that we feed then to the VLM. At the same time, we have a contextualized prompt that leverages the segmented input here, for example, being, hey, VLM, please stay on the path. Don't go on the left or the right. Try to utilize this path as much as possible. And the VLM tries to follow these prompts by iteratively setting a waypoint. So after the VM puts down one waypoint, we take this kind of interim solution and feed it back to it. So it kind of knows where it was and kind of build up this history until it reaches the goal. And this is the idea behind this approach. We see later on we have different kind of iterative versions or kind of deviation from these. For example, we have an iterative raw version, which kind of skips the whole pre-processing input, but also have an iterative selected version that kind of is a hybrid between blue noise sampling and this kind of approach, whereas like it generates with blue noise sampling points around this waypoint and then let the VLM choose one, and after it chooses one, it generates others. And these kind of approaches are shown here in order to kind of detect how segmentation and in general the iterative approach can benefit the VLM's planning. So since VLM, and especially in off-road environments, there's more than one solutions, so meaning there are open-ended answers, we need to have a benchmark that kind of assess these kind of solutions or proposed path. And a benchmark is good because, or is only good if the metrics are good. And in our case, we are really interested in, first of all, kind of having the path quality, because as of right now, we are measuring the kind of path quality against one single human annotated ground truth, as well as seeing the research efficiency what these kind of approaches have, because we're really interested in real-world applications. So therefore, for the path quality metrics, we have, for example, the Foresight distance, which kind of measures the deviation between the ground truth and the proposed path, as well as having resource-efficient metrics such as query time, total query cost, in order to assess if this kind of approach or VLM in general for long-range path planning is even feasible for a real-world application. Okay, now that we've done with the metric side, on what do we test them? And for this project, we have in total 20 scenarios consisting of 13 real-world environments from different settings like urban and off-road, as well as 7 simulated from simulation. The kind of idea behind these kind of scenarios is to have a lot of diversity in the environment and the semantic cues, etc., in order to kind of test how generalizable the approach is when utilizing VLM for long-range path planning. So at the end, we total with 200 different individual scenarios, which can give us a kind of trend where or which approach is more suitable. And for this, we get these kind of benchmark results. So at the bottom, we have the resource efficiency, and we see that over all these kind of methods, we kind of have a constant. So meaning that despite being iteratively and querying the VLM multiple times, we do not take more time in our approach or be more costly, which is a kind of good thing. Also, when we see the average Foresight distance, like I said, the deviation to the human ground truth, we see, of course, that the manual one is the best since the waypoint placement are mostly the best in these scenarios, that we kind of come close with our iterative segmented approach. Whereas like this naive sampling kind of does not perform well since it does not include the semantic cues that the image delivers. So this is a good sign for our approach that is feasible. So now to the image. So to kind of have this understanding in the visual sense. So as we can see, the kind of manual or human place waypoints kind of pushes the VLM into a certain way of thinking. So meaning we get a good results and therefore the best performance. At the same time, we see with the kind of naive sample one that this kind of sampling um, kind of limits the VLM in the sense that it can forces it to not follow the prompt. For example, in this case, hey, follow the path as much as possible in order to reach the goal. So therefore, we get these kind of zigzag movements or non-trivial solutions. At the same time, with the raw image, raw iterative version, waypoint generation, meaning having no segmentation, just giving this image to the VLM, we see kind of the hallucination that VLM kind of have. So it just hallucinates a straight path and stops at a certain point because it thinks it just reached the goal. So these kind of things show us that there has to be that the segmentation, the contextualization of prompts is really crucial in order to have better segmentation. You can see here, for example, in this kind of scenario that the waypoint generation or that the VM tries to be as much as possible in the path, and after that kind of deviates from the path since the goal is on the right-hand side. So therefore, we see that our iterative segmented approach is feasible for these kind of planning problems. In conclusion, we can say that with this kind of project, we first of all have with the iterative VLM planning on segmented mass a better reasoning through combining segmentation and iterative planning in the sense that we ground the VLM, but also have a first comprehensive benchmark for long-range planning that encompasses different scenarios and environments and vehicles. And for the future work, we would like to add more VLMs in order to have a better apple-to-apple comparison through different like commercially available VLMs and also kind of test out how scene-specific prompts might be able to get better results, as well as incorporate multiple human-annotated ground truths. As you saw in the results, we have had high standard deviations, but this is kind of a flaw in the benchmark design, since in off-road environments, you have a lot of different paths that are feasible and transversable. So therefore, when the VM proposed a good alternative way, the benchmark does not kind of measure that appropriately. So therefore, there has to be a multiple human annotated ground truths to kind of counteract this. Also, what we want to try in our future work is to further investigate on hallucination mitigation techniques. So kind of going from the segmentation mask into other kind of things in order to ground the VM, as well as incorporate spatial temporal reasoning into the benchmark. And lastly, for the presentation, some generalizable insights for using VLMs. In general, what I've noticed when working on the project is that one should always try to leverage the information that is already out there. So kind of ease up this kind of problem for the VM in order to have it not plan everything in one step, rather to have it easier broken down. Therefore, you can kind of avoid these problems with hallucination and therefore make the problem easier for him. Also, for like kind of debugging and in general understanding the problem, just print out justifications. They most likely will help you or kind of push you into thinking like the VLM and therefore kind of helps you in certain scenarios. Last but not least, I would like to express my gratitude to my both mentors, Scherer and Yifei, as well as the Sebastian and Wenchen from the lab, in general for giving me this kind of exceptional experience here at CMU and having these kind of technical discussions and therefore being able to learn a lot, as well as of course, the off-road team and the entire air lab for being so polite and being welcoming and being able to integrate very well and very fast in their lab. Also, I would like to express my gratitude to Rachel and John for even organizing the RIS. It has been incredible, and this summer it was something that I will never forget, and therefore I'm um, deeply, deeply express my gratitude for this, as well as, of course, the German Academic Exchange Service for even funding this stay and being able to be here in the US, especially here in Pittsburgh. Thank you very much for listening, and I hope you have a great day.